Welcome back. The year is 1912. J.J. Thomson and his assistant, Francis Aston, are firing a stream of neon ions through a maze of electric and magnetic fields, and they're striking a photographic plate on the other end. What they are about to discover will shake our understanding of the atom, give us another puzzle to solve about atomic structure, and launch an entirely new way of analyzing matter that we still use today, mass spectrometry. Here is how their experiment worked. Neon atoms were bombarded, likely with electrons, in order to ionize them. This means that electrons were stripped off of the neon, turning them into positively charged ions. The beam of neon ions was passed through a slit and into electrically charged plates. Now, something happens to charged ions when they pass through electric and magnetic fields. They don't travel in a straight line, but their trajectories changed. And they change based on the mass to charge ratio. So if we just assume that everything has a charge of +1, what's going to end up happening is that the lighter ions are going to be deflected more, and the heavier ions are going to be deflected less. Now, in this magnetic field, something similar happens. We are separating them even more based on their mass to charge ratios. So when they hit this photographic plate, we can develop the photographic plate to see an image of where our streams of ions hit. In other words, we now have a way to measure the mass to charge ratio of ions. What Aston and Thomson expected was one single straight line on this plate. Just one kind of atom with one mass. But what they saw were two. There were two distinct glowing regions for neon. This was not noise, it was not error. This meant that neon, an unreactive noble gas, existed in two different forms with two different masses. In other words, neon has isotopes. At this point in time, we already knew a few things about atomic structure. We knew electrons orbit a dense nucleus. We knew atoms are mostly empty space. We've had the periodic table since the 1860s, and we even knew that atomic mass was somehow important in determining the elements. But if neon atoms can have two different masses, what exactly was in that nucleus? Let's fast forward 20 years. It's now 1932. Another British physicist, James Chadwick, is puzzling over a mysterious kind of radiation coming from beryllium that's been bombarded with alpha particles. He called it gamma radiation, and it had some very unusual properties. So for comparison, alpha particles are heavy and they're positively charged. We now know them to be the nuclei of helium atoms, and they can be stopped by just a sheet of paper. Beta particles are light, they are charged, and they can be stopped by just a few millimeters of aluminum. We now know them to be electrons or positrons, but gamma radiation was different. It was uncharged, it penetrated almost anything, and what was it? So here's what he did. He had a sample of polonium. Polonium is a radioactive element that decomposes and gives off alpha particles through this equation. So polonium-210. Polonium has 84 protons in the nucleus. It's element number 84, and this particular isotope has a mass of 210. This decomposes to lead, 206, and helium nuclei. This is our alpha particles. So this polonium was giving off alpha particles. He was directing these alpha particles to a sample of beryllium. Here is the reaction that occurs when beryllium is bombarded with alpha particles. So we have beryllium-9 being bombarded with alpha particles, which I am calling helium-4 in our nuclear equation. And the reaction that's occurring is a nuclear reaction. So we get carbon-12 and this mysterious gamma radiation. He now had a way to generate gamma radiation and direct it at a lot of different substances. And that is exactly what he did. He directed this gamma radiation at helium, at hydrogen, at nitrogen, at a lot of things. But something really interesting happened when the gamma radiation hit a hydrogen-rich material. Specifically, he used paraffin wax. Here's what happened. When gamma particles hit the paraffin wax, protons were ejected. By the way, the nucleus of the most abundant isotope of hydrogen, hydrogen-1, is just a proton. So paraffin wax's protons were being ejected. This was the exact clue that Chadwick needed to figure out what he was dealing with. So using the laws of conservation of energy and momentum, he realized that gamma radiation has to have a very similar mass to the proton. And since it was being ejected from atoms and it has a large mass, that means it must reside in the nucleus where most of the mass of the atom resides. So we have a new subatomic particle. Gamma radiation is also known as the neutron. Our mystery from earlier about the two different masses of neon is explained by this new subatomic particle. These are the two different isotopes of neon that were being detected. Because they're neon, they each have 10 protons in the nucleus, but the mass number, the total number of protons and neutrons, is different. So neon 20 has 10 neutrons, neon 22 has 12 neutrons. Join me next time as we explore the quantum mechanical model of the atom. Thanks for watching Chemistry in a Nutshell.